All right. Let's see. Make sure. Let me pull my microphone over here a bit. There we go. That's better. Hope everyone had a good weekend. Nice long weekend. But with that, welcome to the class, everyone. My camera's a bit off center today. There we go. Hope everyone had a good weekend. To that end, just getting started with some usual announcements. Quiz, I believe it's up to 5, is due tonight. That is the quiz on algorithms and recursion. There will be a quiz tomorrow, and the quiz tomorrow, I believe, is the last quiz, but no, there might be 2 more. I'll have to look into that. I can't actually remember what the course schedule says. Whatever the course schedule says, that's what I'm going to do. Homework 4 is due tomorrow. There's a bit of confusion on that because I made the webcat due tonight. That was unintended. The homework was intended to be due Tuesday night, so that is tomorrow. That said, based on my office hours last week, I think most, or at least pretty much everyone I've talked to, more or less, is done or close to done, which is good. That was a Colby Bear just now. Homework 5 is released today. It is the last homework. It is on today's lecture, and we're actually going to spend a fair amount of time today talking about that homework, just to make sure everyone is prepared. Today's lecture is on linked list, as we'll get into in just a second. Yeah, so are there any questions about anything that's going on? Just getting my whiteboard camera set up. Cats. They pulled on the cord as soon as I set it up. Work. Alright, sorry about that. Are we getting any good jokes today, McBurney? If they come to mind. I to be honest, I do not plan my jokes that much. I was always kind of a class clown. So, there we go. Sorry, I was just making sure that the whiteboard camera was set up well. Other than that, obviously the big thing on everyone's mind is the final exam. It is Saturday, so just to outline the week. Today we're talking linked lists. Then on Tuesday, intro to trees. And I believe we start with heaps. Then from there, Wednesday, binary search trees. Thursday, I've updated it. It's going to be generics and exceptions. And then finally, Friday will be an exam review. The exam itself being Saturday. As I said, I can't start the exam before our scheduled time, so the exam will be 1 p.m. Eastern Daylight Time to 11:59 p.m. Eastern Daylight Time. It will be 2 hours in duration, so that means that you should budget 2 hours sometime during that, keeping in mind that this means that you will need to start the exam before 9:59 p.m. In order to get the full duration. A note on homework 5. Homework 5 is it is due Friday night. However, and it's a fairly short assignment. The code can be complicated, but it's not. However, it can only be accepted up to 1 day late, and the reason is I need to turn around final grades quickly, and so as a result of that, Saturday night at 11:59 p.m. or at 11:30 p.m. I should say, it will not be accepted. So just be aware of that. You can only submit this homework 1 day late. Is it back end heavy, or is the exam going to be based on the whole class? Back end, it is heavier on post exam 2 content than it is on exam 1 content. However, given how much of exam 1 was on understanding the basics of Java, that certainly means that that material is necessary to understand the material we've discussed. For example, if you're not familiar at this point with objects or stack and heap or concepts like that, you're going to struggle when we talk about data structures. If you're not familiar with functions, certainly you're going to struggle with recursion. So it is heavier on back end content, but not devoid of any pre exam 1 content. Are there any that's about as specific as I can be. If you ask me for a percentage, I'd say it's somewhere between like 60-40 and 80-20, and I know that's a wide range. With the larger number being post exam 2, and I know that's a wide range, but that's just, again, some questions are necessarily kind of foot in both. How long is the exam again? It will be a 2-hour duration. So let me make sure I can scroll this. It'll be a 2-hour duration. I don't know how many questions it has yet. Again, one question is not a good unit of measure. There were some questions on exam 1 I'm sure took everyone in the class less than a minute, and some that took more than 5. And they could have both been multiple choice questions, so. But it will be a 2-hour in duration, so that's how much time you will need to budget on Saturday. It will be done structurally. It will be as similar to exam 1 as feasibly possible, which is to say mostly form questions, 80-20 breakdown of form questions to coding questions in terms of points. It will be open note, open book, open IDE, open internet, for the same reasons that I said before, as well as Stack Overflow, Chegg, etc. will be banned. I should note that while this didn't happen this term, I do monitor Chegg, Stack Overflow, pretty much every resource that I can that day, and it's because we have seen students in CS upload entire exams the day of the exam to online resource websites. And what we have done is we have reached out to those websites to tell us which accounts access them, and then we fail those students and submit them for an honor code violation. And while the honor code has not met on those cases yet, we fully expect expulsion. And I say that to say hopefully it's completely unnecessary. It appears to have not been so far. But yeah. Last thing is, this is the final homework assignment. And again, can only be submitted 1 day late because it's due Friday night. That said, I would say this is a shorter assignment. I think the total amount of code writing for most students will be less than 50 lines. But it's similar to homework 4, where you don't write a lot of lines of code, but the lines of code that you write can be a bit tricky and require a good understanding of the material that we covered in class. Any questions about the announcements today? Similarly, I have got the homework 0 through homework 3 grades up on WebCat, as well as the midterm grades, as well as all the in-class activities that are graded until now, as well as all the quizzes that are graded until now. So you should be able to start getting a good understanding of what your final grade will look like, keeping in mind that the final exam is 22.5%. So just be aware of that. And again, I mean, the final goal of this class really is just to prepare you for 2150, and I've not hidden that from the beginning. That is, I'm trying to make sure that you have the knowledge needed and to succeed in the next course. And so, to that end, I mean, if you do cheat in this course, which again, given how broadly I've allowed the acceptable things to be, you'd have to do so very intentionally. If you do cheat in this course, you're just setting yourself up for failure in 2150. So just be aware of that. And again, I haven't seen any reasons to believe that has happened. I just want to address it ahead of time. All right. So today we're going to be discussing linked lists. So up until now, in Java, oh, hang on, that is homework 5. Well, I want to leave that up for now, but we'll come back to it later. With linked lists, the idea is that there it is. The idea of a linked list is that rather than representing our data in some organized set, or can we get a GUI bonus class after the class is over? Tell you what, if you make a post on Piazza, and if 10 people upvote that post saying, hey, we would watch a stream that you did on Monday, July 13, that would not be part of the class, would not affect the grade, but if you get 10 good comments on it saying that people would want to see GUI, I will happily do it. Is the GUI class from the spring still available? I can link it, yeah. It's actually, I think it's just on, I think you can just view it on my YouTube channel. Although you won't have the files. And I would want to upload. Tell you what, here's what I'll do. Same rule applies. I will do a live synchronous lecture like this next Monday if you post on Piazza and like 10 people upvote it, just because I don't want to do it for just one person. But if there's enough interest, yeah, I'm happy to do it. It's not like I'm doing anything else this summer other than every other part of my job. But I will find time. I'll spend a couple hours doing it. And I can upload my code to Colab regardless. I'll try to do that. Just understand that it won't be obviously course material. This would just be more FYI for people who want it. And certainly if you wanted to try to practice with it and get my feedback, I could provide it. I just it doesn't neatly fit into 4 weeks, so that's why I cut it from the lecture material. So yeah, I'd be willing to do it. Anyway, today though we're going to discuss linked list, and we've talked about how there is this thing called linked list. I'm just going to quickly demonstrate how we have public static void main string args. And we've talked about how we have 2 list implementations. So let's say I have list integer L0 equals new array list. And I can import those. And we've also talked about how we have this linked list. And computationally, I've shown the advantages. A linked list is much faster at adding to the front. It's about the same speed as adding at the end, but it's adding in the middle. Linked lists are really, really slow. But you can add and remove from the front in constant time, whereas with an array list, that process is linear time. So why are linked lists like that? Why are you the way you are, linked list? What happened to you as a child? Well, the reason is because the structure is different. You see, when we think of an array list, really, we just model it as an array. So, my array will contain values, but that's because I understand that underneath the hood, if I open up the engine of ArrayList, there actually is an array there. That's where the word array in ArrayList is coming from. And so I can think of these values as being in an array, and yeah, that array may have some extra space, but remember how we talked about expand if necessary, grow if necessary with stack and queue? ArrayList has those same behaviors. It will expand as needed. A linked list is different. This is like a library. You go to a library, all the books are organized, and in fact sorted, although an array list isn't necessarily sorted, but there's a place for each book, and you just put the books where they belong. If you're familiar with how the internet works, what happens with the internet is when I'm streaming this to Twitch, It leaves from my computer, travels over network cable to my ISP. That ISP sends it to another ISP. That ISP then sends it. And by the way, there may be extra steps on the way. Maybe that goes from one ISP to another, to another, to another, and then reaches the ISP, the internet service provider, for the server that's in somewhere in Virginia that I'm streaming this through. And it's going to then bounce to the Twitch servers from there. And then eventually, it gets streamed, uploaded, you connect server to server to server, eventually to the Twitch, and download through that. So it's a sequence of kind of chained things. Think of it more like a train. And you may think, well, this is like a train, but it's not, because a train, here we go, it's now art lessons with Will McBurney again. A train is going to look like this. Oh wow, this is turning out so well. The idea is we have a look. Stuart, you're not helping. Stuart has stolen my seat. All right, I'm gonna have to get that back in a bit. The idea of a train is that the locomotive is not attached to every single car on the train. Right? If I have multiple cars, the locomotive does pull all of these cars, but it's not attached to every car. Rather, the locomotive only pulls the car directly behind it. And this car then pulls the car directly behind it. And this car pulls the car directly behind it. The locomotive is not attached to every car. I can't go directly from the locomotive to the caboose. I have to go one car at a time. And so the idea here, where did my... That's knocked my eraser over again. There it is. And so the idea here of a linked list is basically every value in the linked list is like one of these train cars. It both contains whatever is being shipped here. It has some amount of contents. So this is part one. This is the value that's being stored. And then it also has a connection that tells me where the next car is. That is responsible for connecting to the next car. This is what we call a node. And the idea of a linked list is rather than having one collection that everything is stored in, we have a bunch of different connections. Each connection contains one piece of information, exactly one piece of information, and then a pointer where to tell me to find the next piece of information. Are there any questions so far besides how did they let me out of grade school with this level of artistic talent? My parents paid someone off. That's how I got out, in case you were wondering. But are there any other questions here? See, there were going to be jokes today. Okay, so now I have to get a kitten out of my seat. He's not happy about this. All right. Does it have indexes? That is a great question. It does not. And we'll talk about how it does not have indexes soon. Now, I want to be clear. Let me take that back. We can index it. We can index it. But it by itself, the notion of indexes doesn't apply here the same way it does with arrays. A linked list still has order. It still has a first element, a last element. All the elements are numbered between, but I cannot just say, go to the third point. And we'll see that in the slides here in a second. So, again, the idea of a linked list is it's going to look something like this. This is the front. The next tells me where to find the next value. So these green arrows are the next. And the blue boxes are the values. So if this were a linked list of strings, it could be something like linked list of strings. To jump to your question, TNU, it is Uh, linked lists can be singly linked or doubly linked, and if you're familiar with the difference, I will tell you that java.util.linkedList is doubly linked. If you're not familiar with the difference and didn't understand what I just said, don't worry. We will get to that difference later. Any other questions at the moment? Okay. So again, we have this node class. It contains a value and a next. So one piece of information and where to find the next piece of information. And we can define this as we do here in a class like int node. The int node, which I have already in Eclipse, and you can download this today. You don't need to wait for me to upload it later. I've tried to be pretty good about that. The int node class, and I have getters and setters for this, so don't worry too much. For the sake of simplicity, I've made these public. You can make them private, but we're going to talk later about how often our node... can there be doubly linked lists? Yes, certainly there can. If you're familiar with the difference between singly and doubly linked lists, I will get later to how a doubly linked list is implemented. But for now, we're starting with singly linked. And if you're still not understanding what I mean by singly and doubly, don't worry. We will discuss that difference. For now, it's worth noting this is singly linked. That is to say, every node contains a value and a pointer to the next element. So when I create a node, I'm going to create that node by just passing in the value, and by default, I'll say next is null. But since these are public, I can directly manipulate the values. And if they were private, I could simply write getters and setters like I have here. But this is my starting point, int node. And again, the idea of the node class is that it allows me to link things together. So if instead of an array, I want to do a linked list of numbers, I could have 8675309, where the first node contains the number 8 and points to the next node. The next node contains 6, which points to the next node containing 7, and so on. So in this case, 8 would kind of be the locomotive. It would be the front that is pulling everything else, or attached directly only to the next node, but indirectly to every other node. And so this linked list combines these nodes, chaining them, much like a train. You know, each locomotive pulls the next locomotive. They're coupled together. It combines them into a series of nodes into a list. Now, in order for this to work, we're going to have to keep track of the first node. And we're going to often call this the head node or the first node. You can call it many different things. Head is the nomenclature I'll use today. So this head node, again, is used to connect only directly to the next node, but indirectly to every other node. Now, as we've said, every node has to contain a value and a next pointer. Does that mean that our linked list has to be eternal? It has to be infinite? Because after all, even the last node has to adhere to this. How do we identify the last node in a linked list? How do I identify the last node here? What unique feature is there for the node that tells me this is the end of the list? What about null? What points to null? Because remember, there's two part. I see what you were saying there. I apologize again. It censors anything with a dot in it. Specifically, this node's next pointer equals null. Not the node's next pointer. Because remember, a node is always two things, a value and a next. Very specifically, the next points to null. There is no next. The value is not null. That's important to understand. So we wouldn't use getLink. We would use getNext or just .next because we made next public in this case. So from there, give me 1 second here. So from there, we can now look at this list and we can say, okay, so if I wanted to get to, let's say, the node containing 7, how could I get there? Well, if I wanted to get, can you use an anonymous class? Yes, you can. And in fact, later on, actually an anonymous class probably wouldn't work. You'd probably have to do an inner class. I do it with an inner class later. An inner class and anonymous class are different. And I don't think you could do it with an anonymous class. I'd be very open to being proven wrong there. But you can do it with an inner class, yes. And I do it with an inner class later. But for now, just to introduce one concept at a time, this is my node class. Now, this is not a list. A list is not a node. They are two different things. That would be like saying a tire is the same as a car. A car has 4 tires. A list has multiple nodes. But a node is only one piece of that. So now I can define another class, let's call this linked int stack, that contains a head node and manipulates the node in some ways that we're going to look at in just a second. So from there, if I wanted to get to the node containing 7, how could I get there? Well, I cannot just say, give me the 3rd node. Now, if I'm using the linked list interface, I can, but that's because the linked list interface has implemented a method called get, which we will talk about later. Instead, I access a node indirectly. So, for example, if I want the node containing 7, I would say head.next.next, which gives me this node. Now, to be clear, it gives me the node, not the value. Head.next.next is not 7. It is this, the node containing the value and the next. So if I did head.next.next.value, that would give me 7. Can you also implement an iterator? Sure. Sure. You'd have to implement your own iterator if you were building your own linked list from scratch. Like a stack, I'm not sure what you're asking. We can implement a stack with a linked list. We can implement a queue with a linked list. We can implement a list with a linked list. So we can implement any type we want. So is next like top? I forgive me, I'm not understanding what you're asking, but my intuition says no. Next is whatever node I'm at, next is the next node. So if I'm at the head.next gives me this. If I'm at head.next, this node.next is this node. This node.next is this one. It only gives me a next node. It doesn't give me the last node. So don't think this is like a stack, because we're describing something that can be used to implement a stack, and we'll show that later. But this by itself isn't necessarily a stack. It would be like saying we can implement a stack with an array. Arrays are not stacks. Arrays are just arrays. We can implement a stack with an array, but that doesn't make arrays be stacks, if that makes sense. Now, to be clear, the linked list will not keep track of every node directly. It will always keep track of the head node. Or I should say, I mean, any linked list operation I've seen will keep track of it. We'll talk later with Doubly how in theory you wouldn't need to, but I've never seen it implemented without keeping track of the head node. Similarly, we can optionally, not required, but it will help later on, keep track of the tail node. That is the last node. And we'll talk about this a bit later on. Specifically when we're implementing a queue. But understand, a node isn't a value. It's a value and a next. So if you want to get the value 5, it would be head.next.next.next gives you this node, but then you have to go one step further and say .value to get the value contained inside of the node. It's like a walnut. You need to actually open the nut up before you can get to the tasty, tasty walnut meat. And that is actually the term for it. I don't know why. So now let's try to implement a stack with this linked list. Now again, I can implement any kind of list I want. Stacks, queues, a generic list. For now, and only for now, we're going to implement just the stack. So if I want to implement a stack, what would I do? Well, first, let's go ahead and let's start by just... I'm going to leave in the toString for now, but I'm going to come back to this a bit later. So initially, my constructor, when I create a list, I create a list to be empty. What do you do if you don't know the placement of value you want to find after the head? You would write a find function, and we're actually going to do that later today. So we are going to write a find function later. For now, let's just try to stick with something simple. A good starting point is a stack. It has a very few number of operations, all of which are constant time and don't require loops. So let's start there. So initially, we need to define, and I can define this as private. We define an int node head. And when we call our constructor, it creates an empty list. It creates an empty list. From there, let's consider how we would do public void push int value. Now notice, I'm pushing a value as an integer, not a node. That means we're going to create a node. So, let's take a look at this. I have a little, nice little animation for you here. The idea is, first, if we're going to push, we need to define a node that contains that value we are pushing. So that's what this node is. And initially, its next value is null. We haven't connected it to anything yet. So here's how we do this in code. We simply say int node, because that's the data type we're creating. New node is the variable name. It doesn't have to be new node. I could call it Steve if I wanted, but I'm calling it new node. Equals new int node value. This creates the new node. That's step one. Step two, we then need to say that the new node connects to the first node. That is, say we're attaching this to the front. And if you think, why aren't we adding things to the end of the stack? We're treating the front of our stack like the top and the end of our stack like the bottom. There's reasons for this that have to do with computational efficiency, which we'll get into when we talk about Q. For now, just accept the reality that the bald guy hath decided from his chair upon high that the front of the linked list will be the stack in his inscrutable ways. So I'm going to say the new node.next is the head. That connects it to the front of the linked list. So to do that, I simply say, and I can do this multiple ways. If I have a setter, which is what I illustrate in the code I uploaded. If I have a setter, hang on. Oh, I'll write that function later. Then I could say new node.setNext equal to head. That's one option. What if the head is null? Great question. We'll get there. Another way to write this, if I wanted to directly access the values, if I made next public, I could say new node.next equals head. That would also work just as well. If next were public, if it's private, I would have to do some kind of setter like this. So to illustrate again what I'm doing here, I'm just drawing this yellow line. This yellow line right here. I'm making that connection. There you see it. From there, I then need to update the head pointer because I have a new front of my list. And so I simply say head equals new node. And now you can see that this purple node is the front of my linked list, and it allows me to access all the values that were previously there indirectly, but this is the new front of the linked list. So new node, head equals new node. And it very specifically has to be done in this order. Are there any questions about the push function? And I'll pull the slide back up just because it has the code there as well. Are there any questions about the push function other than what if the head is empty? Because we'll address that. I'm very glad you think this is cool, by the way. Alright, so that's how we push to the front. We'll talk in a bit about how we remove from the front, because this is a stack, and so whatever side we add to, that's the side we have to remove from. And so, how do we first detect if this linked list is empty? Let's write another function. Public boolean is empty. That takes in no arguments. This is going to return whether or not our linked list is empty. When is our linked list empty? Well, let's consider this next slide. Which of these two is empty? Well, it's obviously 2, right? It's obviously 2. Because this list has stuff in it. So this list on the right is empty. So all we need to do for is empty is just return head equals null. If head is equal to null, this returns true. If head is equal to false, this returns false. So there we go. That's simple enough. Any questions about is empty and why that works? So now let's take a step back and let's say, okay, what if head is null? That means our list is empty. Would this function work if our list was empty? Well, think about it. Head would be equal to null, right? So we would just be saying, because this is the only place we reference head, its previous value, if the list were empty, we would just say new node.next equals null, which is fine, because if the list were empty and we added one value, that value is both the head and the tail, right? It's both the first and the last value because there's only one. And so, as a result of that, saying new node.next equals null is actually completely fine. There's no problem with that in that case. And if it's not empty, then this will set it to whatever the head was. That isn't null, and that's also fine. So it turns out that we don't need to modify push if the list is initially empty. I can diagram that out real quick just to clarify. Again, just to illustrate dynamically what we're doing. I have two linked lists. And I'm just drawing them inside of these boxes. I have this one where head is just null, and this one is empty. And I have another one where head points to 8, 6. We'll say null, so it only contains 2 values. If I were to add 7 to both of these, just following the same formula, so I'm pushing 7, and I'm using red to illustrate the difference. Let me make sure that shows up okay. Yeah, that shows up fine. So I create my new node, which contains 7. That's step 1, and I do that in both places. New node, 7. I then say new node.next equals head. And then I then say head equals new node. So I erase this. And you'll notice that in both cases, I end up with a valid linked list. The red is showing what changes as a result of that. Are there any questions so far? The red actually shows up very well. I might have to use it more. All right, now that I actually have markers, I had to buy some, but yeah. Okay. So we've done 2 of the 3 we want to do. The last one we want to do for now is public int pop. And this is going to pop off the linked list, the front value, and return whatever is there. So is the head... So does head point to in the null point to nothing? Hang on. Does the head in the null? Forgive me, I don't know what you mean by the head in the null. The head in the empty list points to null. But that is because there's no value to point to. And remember, null, when we talk about it, null doesn't mean nothing. Null means nowhere. So if I have no values, so again, in that first list, head is not pointing to nothing. Head is pointing to new node now. Before it was pointed to null, but that was because the list was empty. That is the definition of an empty list. There was no first value. The first value was nowhere because there wasn't one. So head right now is pointing to the new node containing 7. All right. So we're going to do pop. This is going to return the value. So let's see how this is done. The first thing we need to do is we need to store the return value to be returned later. Because after we do what we're going to do, the value won't be accessible anymore. So the first thing we need to do is we need to create a return value. So let's do that real quick. Int out equals head dot value. This is the value to be returned. The next step is we need to update our head pointer to remove this node. So we update the head pointer by just saying head equals head.getNext or .next, whichever is used to access the next value. So update the head pointer. Head equals head.next in this case, or getNext, you could do either. And then from there, we can simply, at this point, return out. Or, in the case of what we did on slides, return value being the name of the variable. And you may think, but wait, we're not done yet. We haven't deleted this node. Actually, we have. The thing is, when you remove any access to a value, Java frees that memory. And so you may be thinking, well, wait, what happens to the node containing 8? It's not out of scope. I don't want to say that. It's that it's unreachable. Because I can say head.next to get to the node containing 7, and I can say head to get to the node containing 6. There's no way to reach this node anymore with the variables I have. There's no way to reach it. So scope isn't the right term there. Rather, it's just unreachable. There's no way to access where that is stored anymore. And as a result of that, what happens is Java garbage collection comes along, and it says, oh, well, hey, we don't need you anymore. And let me see if I can... Here we go. This is what happens. And it's gone. I'll show that again. It just disappears. Does it still take up space in memory? No. That's what Java garbage collection does. It recognizes that this memory is no longer used. And so because this memory is no longer used, because it's not reachable, it's wasting space. So Java garbage collection frees it. If you're coding in C++, yes, that is different. Java has built-in garbage collection. It will remove any memory that's no longer referenced. I believe Python has garbage collection as well, but I will say that I'm not certain of that. C++ very, very much does not have garbage collection. And that takes me to an anecdote. There's a classic Nintendo 64 video game called Donkey Kong 64. And Donkey Kong 64 had a bug. And this was very much intended to be a bug. See, the game would allocate memory for the graphics, for the character HP, for all kinds of things. When you allocate memory, but you don't release it back to the computer when it's no longer useful, that is called a memory leak. Because your program will need more and more and more and more and more memory until eventually it just crashes because there's no more memory available on the computer. And in Donkey Kong 64, they had a bug that caused a memory leak that would cause the game to crash in about 30 minutes of play, and they couldn't fix it. And they still had to ship. This was back in the cartridge days. Making cartridges was much more time-consuming. So they couldn't delay the game. They didn't do the CD Projekt Red approach of just delaying the game forever and ever and ever. Rather, they had to release the game. So their solution was, and if you've ever played Nintendo 64, you might be familiar with something called the expansion pack. The expansion pack, what it did was it replaced the memory chip in the Nintendo 64 with a memory chip that was significantly more massive. It had a lot more memory available. The memory leak was still there. So on a actual Nintendo 64, if you were to play Donkey Kong for like 12, 14 hours straight, or you just rapidly went back and forth between different areas, you could crash the game in a few hours. No, you didn't have to buy the DLC. The expansion pack, they actually shipped it with the game. Because it was such a flub, like in terms of the production, they knew it was going to be such a problem, that if you bought Donkey Kong 64, you got a free expansion pack. This was a little bit different then. But so the way they actually fixed their bug was the same way that we address global warming. We just kick the can down the road and figure, we'll deal with it then. That was how they dealt with the memory leak. In this case, you don't have to worry about memory leaks in Java. You don't. Java basically makes it impossible to have memory leaks unless you very, very, very badly design your code. Whereas in C++, which most video game development really is done in C++, no, because Donkey Kong 64 was a good game, and global warming is fucking terrifying. Forgive my language, but that word is warranted there. Donkey Kong 64 is actually a pretty good game. Anyway, point being, you don't have to worry about memory leaks in Java because of this garbage collection process. Because, that's not going to work out. Because when the memory is no longer referenced, it just gets snapped out of existence. This is part of the 50%. No spoilers. No spoilers in chat. Disappears. So, you don't have to delete it, you simply have to dereference it, and it will disappear. And so that's it, we're done. This is our stack. Now, I have written a toString method. I don't want you to worry about it right now, how it works. Just trust me that it does. And then from there, let me real quickly implement size. Don't worry about how I'm doing it. We will get there. Public int size equals 0. Return size. And then for int node t equals head, t not equal to null, t equals t.next. Don't worry about this. I will explain it later. Just trust me that this works. I have to do it in order for my demonstration to work. So you can see we start by pushing. We start with an empty value. So is empty is true. We then get the size. The size of the empty is 0. I print the stack, and it's just head is null. From there, I push 8. I print, is it empty? No, it's not empty. What's the size? Should be 1. It is 1. I then push 6, 7, and 5. And you can see that when I print my stack, because I'm pushing at the front, it's not 8, 6, 7, 5. It's 5, 8. Yeah, it's 5, 7, 6, 8. It's reverse order of that. I then get the size, should be 4, and it is. I then pop, which should give me 5. It does give me 5. That's the first value. I pop the next value. It should give me 7, because with the 5 removed, the 7 is the first value, and I get that. I then print the stack, and you can see the stack, because I've popped 2 values, has shrunk to 6, 8. I then do 2 more pops, and I check, is this empty? It is. And if I print the stack, you'll see it's null. Now, one thing I do have to worry about is if I pop one more time, stack.pop, I'm going to get a null pointer exception. And when you're working with linked lists, when you're doing the homework, fair warning, you're going to see that a lot. Sorry, the camera's reversed for me, so it breaks my brain a little. So this null pointer exception means that you tried to do something null dot something else. Basically, because the head is null, I cannot use this line of code, because there is no value. So if I try to pop from an empty list, it's going to crash. And I'm actually going to say that I'm okay with that. I'm not going to try to fix that, because this is a user error. Like, my list works fine. You're the one who's trying to pop from an empty list. That's your fault, not mine. Why would you ever try to pop from an empty stack? That doesn't make sense. So I'm going to let this be something that causes a crash, because you just can't pop from an empty stack. What could I return? I can't return null, because this is an int function. So I'm just going to let it crash and let it be the user's own fault. Any questions so far about the stack implementation before we jump onto the queue implementation? Could we put a try catch there? I mean, the user could put a try catch there. I'm not going to put a try catch in my code. Because here's the thing, like, I could catch a null pointer exception. By the way, we're going to talk about try catch on Thursday. But a brief preview of that is you should only catch exceptions if you can do something with them. Like, okay, they try to pop. Yeah, I'd more likely use a throws. I'd throw a new exception. Something like you tried to pop from an empty stack. Don't do that, stupid. And if you're familiar with those, that's fine. If you're not familiar, we will get into that on Thursday. But something that is a general rule of thumb is that you should only try to catch exceptions if you can actually do something with them. Otherwise, you should just let the program crash. Generally. There's some exceptions as it relates to checked exceptions, and we'll talk about that on Thursday. But for now, we're just going to say, hey, you popped from an empty stack? That's your own fault. That's on you. That's not on me. All right. So now I want to quickly define why we're calling what we've been doing a singly linked list. And we're calling this a singly linked list because each node has one link, one node link next that points to the next value. As a result of this is a one-way street. I can very easily go from left to right. I cannot go from right to left. There's no way to tell me what the node before the tail is. Now, I could do a doubly linked list and what that would look like. And let me change the color here. Oh, it's just an outline. Let's change this to orange. And I could flip this and then say every node has both a next and a previous pointer. This would be a doubly linked list, but there's a trade-off. Is that the doubly linked list, A, uses up more memory because we have to have twice as many pointers per node, and B, it makes the code a lot more complicated. So when we can avoid it without losing efficiency, we want to avoid having these orange lines. But this would be a doubly linked list. So this node.next gives me this node, and this node.previous gives me this node. We can implement a queue without a doubly linked list. We can implement a queue with only a singly linked list. Is this still considered a linear abstract data type? I don't know what you mean by so an abstract data type is a broad description of a data type like a stack or a queue. I've not heard this term linear abstract data type before. If that is a term that others have used, I will say that I am surprised by. I guess if you mean a linear abstract data type by something that you can iterate through, you can still iterate through a doubly linked list and visit every value once. Technically, when we get to trees, you can iterate through a tree and visit each value only once. So if that's what's meant by a linear abstract data type, then I guess this would qualify. But I'm not familiar with the term linear abstract data type as a thing. But if that is what it means, then if what it means is you can iterate through the structure and visit everything exactly once, that is, you can write an iterator for it, then yes, this would be that. But that would be more of a data structure than a data type, I would say. Although technically all data structures are data types, but it'd be like calling a square a rectangle. It's not wrong, but you could be more precise. And for those who didn't get that question, don't worry too much. That was me kind of riffing to try to make sure I understood the question. So, given, though, that we want to implement a queue with a singly linked list, because we can do so while still maintaining every option as constant time, InQ and DQ, here is my question. Which do you think is going to be better? And don't vote yet. Pause the voting. The polls have not opened. I want to explain the choices. The first value is when we add a node, we add it before the head, like we did with stack, and we remove a node, we remove from the tail. The second option is that we add values after the tail, but we remove before the node head. Or we remove, I should say, from the node head. So when we remove a node, we would remove 8 first. When we would add after 9. That's option 2. Option 1, if we removed a node, we'd remove 9 and add before node 8. Given that, the polls are now open. Which choice do you think is better? Because one of these is right and one of these is wrong. Which is better, 1 or 2? Vote now. There's 21 people watching. I'm going to wait till I see 21 responses. 1 or 2? If it's faster to add to the head, wouldn't you pick option 1? We're seeing a couple 1s, but mostly 2s. Is it just because everyone's guessing 2 because the first person gets 2? What if I told you right now, maybe the answer is 1? Wink, wink, nudge, nudge, hint, hint. Let's see what votes come in then. Which is it, 1 or 2? Mostly 2s. I'm going to wait for like a couple more votes. Oh, we're down to 19 people. 1, 2, 3, 4, 5, 6. Still not 19. Okay. Need one more vote before we can proceed. All right. So it turns out that the correct answer actually is 2. And here's why it's 2. If I want, and again, this is singly linked list, very important. If I want to add to the end of my linked list, I would simply create a new node. We can recolor it. Let's make it orange. I could add that node here. I would simply say tail.next equals new node, and then tail equals new node. And this, of course, by default, has the next pointer null. And that is clearly constant time, right? It doesn't matter how big my list is, because I have this tail reference. I have a direct link to the last node. So that's good. That's constant time. And if I add to the front, though, you may note, well, the same is true. I could add to the front in exactly the same way. I would just say new node.next equals head. Head equals new node. Both adding to the front and adding to the end are constant time. All right, that's fine. We're good. So there it doesn't matter. But what about remove? That's where the difference is made. See, if I want to remove the head node, it's very simple. I just say head equals head.next. And then this node just gets deleted from existence because there's nothing referencing. That's clearly constant time, right? How would I remove the tail node? I can't easily, because I can't say tail equals tail.previous. I can't do that. Because remember, this is a one-way street. You can't go backwards. So if I wanted to find the node before tail, I would necessarily have to start at the front and work my way right until I found the node before the tail, and then I could update this pointer. That would require a loop that visits every element of the list. And so because of that, removing from the tail in a singly linked list is not constant time. It's linear time. Whereas removing the head is constant time. And so because of that, option 2 is the better choice. So now let's go ahead and implement that queue. Let's implement the queue where we remove from the head and we add at the tail. Which, think about it, this makes sense, right? The front of the line is the person who's next to get helped. If you're, say, in line at the DMV, if you've had to go to the DMV in Charlottesville, it is not fun. We have gotten there. They open at 7:30. We've gotten there at 6:30 and waited in line for 3 hours. But the person at the front of the line gets helped first. The person at the back of the line gets helped last. And so we add people to the back of the line, and they leave the line from the front. So from there, we have our string queue. We have two functions, enqueue and dequeue. So in order to get to before the tail, yes. Well, technically n-1 times, because you have to start the head and keep saying .next until you get to the node where .next is tail. So technically that's n-1 nodes you have to visit, not n. But we treat n-1 as though it's no different than n. Because they're both linear, right? If I double in size, n-1 more or less doubles in size. Okay, just wanted to make sure you got that. By the way, this chat participation today is fantastic. You guys are asking really good questions, and I'm loving it. Keep it up. This is great. This is like the best the lecture's been all summer, and you guys have generally been great anyway, but thank you. To that end, it's a lot easier when people participate. To that end, we're now going to implement enqueue and dequeue, so let's go ahead and do that. Earlier it said keeping track of tail isn't required. For a queue it is. At least, let me reword that. For a queue, if you want constant time operation, then it's necessary to keep track of the tail. If you're willing to accept linear time, then you don't necessarily need to keep track of the tail. But if you want constant time, which you do, then you need to keep track of the tail for a queue. You don't in a stack, but you do in a queue. And that's because with a stack, you add and remove from the same side. All right, so let's go ahead and let's implement a queue. I'm going to first do a few things real quick. I'm going to delete the solutions that I have, and then I'm going to re-implement them. So we have InQueue and DQ. Something to note, I added a few things. So first, we're keeping track of not just the head, but also the tail. Second, this class string node is actually defined inside of the class string queue. Let me make sure everyone can see this. You can actually define a class inside of another class. And the reason you would do this is if this class only needs to be used by the queue, which it does. I'm not going to reference string queue in any other class. Outside of this class, if you want to mess around with the queue, you have to use InQueue and DQ, and that's it. Those are your choices. That's all you get. Inside of the class, I can directly mess around with this node class. And that's what I'm going to do. So this is exactly the same node class as before, except instead of an int, it's a string. And instead of it being defined in its own class, I define it inside of string queue. And it's private, meaning that no other class can even know this subclass exists. Which is good. That's actually intended. Again, the idea of how we want to make our software work is we want to focus on the interface. We want to focus on saying, okay, so, how do I drive a car? Well, I have a gas pedal, a steering wheel, and a gear shift. I don't care if the car is a hybrid, an electric, or gas-powered car. I don't need to know. All I need to know is these are the ways I drive it. And that's how we're designing it. So it doesn't matter that this queue is a linked list instead of an array. It still has InQueue and DQ. From there, though, I've also defined this integer size. And what I'm going to do is, as I add and remove nodes, I'm going to keep track of size, so that way the size is accurate. And this will be valuable because I have a function size that returns the size. This makes it constant time. And similarly, I can just say is empty by size equals 0. So when I initialize this queue, head is null, tail is null. And I know we're late for our break. We will take a break after we're done with queue, but I just want to get through that first. So from there, just take a quick look. We can implement InQueue and DQ fairly simply. We don't need to do anything that we really haven't done before. We're just going to illustrate it. And this is the key. On the homework, you are going to work with linked lists. Draw pictures. Picture drawing is a good thing. So let's get started. And by the way, I would encourage you to do the color coding like I'm going to do. Drawing pictures is the best way to address these. So let's say I have a queue, and that queue contains, let me make this a little bigger. Okay, that queue contains a head pointer, a tail pointer, and a size. And let's say right now we have 2 nodes. And this is null here. I know it's not written particularly well. 5 and 7. Head would point to the first, tail would point to the next. If I do, and size would equal 2 in this case. If I do an InQueue here, again, using my red marker for the things I'm changing, I would create a new node. New node. Sorry, no, I'm not adding at the head. I'm adding at the tail. That's my mistake. Real quickly fix this. I would create a new node. Let's say 6, and I know technically what I did was with strings, but we're going to just do numbers on the whiteboard for the sake of size. This is new node. All I need to say is tail.next. I'm going to update this pointer, which is currently pointing to null, and instead I'm going to say tail.next is new node. Got a little black on the marker. Just wanted to get it washed off there. There we go. Cross out that. Instead, it's new node. New node is already pointed to null as its next, so I don't need to do that. And then I just say tail equals new node, and I'm done. That's all I have to do. So let's go ahead and code that. Based on the picture, what did I do? I did first create a new node. String node new node equals new string node s. I then said tail.next equals new node. And then tail equals new node. But there's one other thing I forgot to do. And that one thing is the size is no longer 2. This number is not accurate. I also need to update my size to be 3. And so, when I enqueue, I also need to do size plus plus. But now, here's the one question. What if this queue is empty? Now let's consider the following. Where'd my eraser go? Let's say instead my queue was empty. Head is null. Tail is null. And size equals 0. Well, now I can't say tail.next equals new node. I can't do that. Right? Because tail is null. There is no .next. So first, this is our before. This is what we need it to look like. Let's see what this will look like in the after. Obviously, we're going to have a new node containing whatever value we pass in. Obviously, size is going to equal 1. What will the head node be? It will be this node. What will the tail node be? It will be this node. And then obviously .next is still null. So as a result of this, I have to take a minute and say, all right, how can I make this happen, and when does this happen? This only happens when my queue is initially empty. And if my queue is initially empty, then I can just separate these two concerns with an if statement. Now, to that end, if I wanted to make my code look good, I'm always going to create a new node, and I'm always going to increment size. From there, I simply say, if size is greater than 0, that is to say, if it's not empty, and I could even just write not is empty here. Not is empty, because I defined my isEmpty function up there. If not is empty, then I do what I did before. Else, I can simply say head equals new node, and then tail equals new node happens regardless, so I can simply shorten it to this way. This is designed to write as few lines of code as possible. What is the default? There is no default of isEmpty. I wrote isEmpty. So the reason I'm using the isEmpty function is because rather than compare size to 0, I've already written a function that defines isEmpty, so it makes more sense to use that rather than to re-implement the wheel. So there is no default of isEmpty. So I could do it this way. Can I write tail equals new node? I do that here. If that's what you're asking. But you can't just do that, because you would also have to update the head pointer in the case of the empty. Because remember, with empty, we're not just saying that the tail is the new node, because the first node is the last node is also the first node, we also have to update head. Alright, so before we do dequeue, my throat's actually a bit parched. I need to get something to drink. We're actually at 2:17, and usually we finish our break by now. I'm going to go ahead. I will leave this code up, but I'm going to go ahead and take our break now, and we'll be back at 2:26. It's got to be a little bit shorter because I got a lot to get through today, but we'll be right back. All right, sorry everyone. I am working on fixing the in-class assignment. Apparently doesn't have the file uploaded. Uh, yeah, I accidentally uploaded the homework 5 PDF. Not intended. Let me fix that real quick. And then we will get back into the lecture. I can go ahead and turn the webcam back on anyway. Yeah, Harvard just said their classes are online. So here is what I will tell you. I think that when the plan was made to have the hybrid online offline courses, that the so I'll just level with you that the expectation was that we would largely get the first wave under control as a country, and that at that point, once we hit fall, we'd have a better testing apparatus, we'd have better contact tracing apparatus. We could then do hybrid online in person, um, and really do that. And here is what I will tell you is that we are now in July, and I really try not to be political, but federally we have made no such moves. The testing apparatus is still largely flawed, and the contact tracing apparatus is functionally non-existent. And as a result of that, again, let me just say, you can probably guess my political leanings right now. I am disappointed to say I would not be surprised if a move like that occurs. But I will say that nothing has been told to me behind the scenes. Nothing has been said like, oh yeah, we're going all online. I had a faculty meeting today where we talked about how we would do hybrid. I I'm just telling you that I'm a diehard college football fan, and I am sad because basically everything I'm seeing indicates we won't have college football this season. And I'll kind of let you fill in what happens from there. I don't know this. I have no insider info. I'm just sharing my insights with you. I am not leaking any information. But let me go ahead and make sure I get the today's daily activity up. There it is. Sorry about that. Okay. All right. If you refresh the page now, it should have the my list file, because we are going to do that a bit later. All right. So now we've done NQ, DQ, fairly simple. For the sake of time, I'm just going to copy it, and you can look at it at your own time. But I'm just going to copy it from today's notes. I will highlight the one important caveat, but otherwise, this is functionally not much different than what we've done before. So, first, I have this. This throws an exception if you try to DQ when the when the list is empty. From there, we store the output value from head.value. We just say head equals head.next, same as pop, size minus minus, because we are removing a value. The one interesting note is here, and this is in case you just removed the last value. Because if you did, then you need to make sure that tail is also null. If you don't do this, you're going to have a node that still exists. Just to illustrate that real quick, why that's an issue. Let's say I were to remove the node that I have now. So my current state is this. Size equals 1. If I were to remove this node by saying head equals head.next, which means head is null, I can just say head is null. Then at that point, I do size minus 1, size is 0, but notice tail is still pointing to something, but this should be empty now, right? Because head is null. So I also then want to add in that statement, if the head is null, if size is 0, also make sure that tail points to null as well. So you want to reset it back to empty. All right. So from there, The rest of this is fairly straightforward. But now let's take a look at how printing works, how this toString method works. I'm going to start by taking a look at the slides. How would I loop through a linked list? So how does this print statement work where I print the queue? Obviously, you have and I'll pull the code back up. You have this part is fairly straightforward. I don't think I need to elaborate how this just basically says head is null and returns. This is the part I want to focus on. How does this part work? And let's take a look. So the first thing to take into note is what this looping variable is, where I say string node t equals head. T is what we call a traveling node. It's just going to ride the rails. It's going to go from one station to the next. So at this point, I'm changing the metaphor up. The linked list is no longer a train. Rather, it's a series of subway stations. It was a lot easier for me to say when I taught in Philadelphia, as there are no subways in Charlottesville, Virginia. But I'm sure most people are familiar with the concept. The idea is you get on at one station and you ride, and the way trains and subways work is you have a terminal station where you have to get off. At that point, the train loops back and comes the other way. So this works generally by we hop on at the first station, head. We then visit every node until we reach the end. So let's break down this loop. The loop is we start at string t equals head. We get on at the first station. Our exit condition, like any for loop, we loop until this condition is false. So we loop until t equals null. If t equals null, we exit the loop. Otherwise, we continue. So remember, you continue while this is true. You exit when it's false. And every step along the way, we are simply going to say t equals t dot next. That takes us to the next station. So I loop through the list the first time. I then say t equals t dot next. And what happens is I go to the next station. Then I do whatever is inside of the loop. I say t equals t dot next. And I go to the next station. And I keep doing this until a few iterations later, I reach here. And I still enter the loop at this point. But then after I'm done with the loop, I say t equals t dot next. And t is now null. And at that point, the loop is over. I do not re-enter the loop here. So this is a very simple for loop to remember as a way to loop through every node exactly once. Okay? So from there, are there any questions about this loop structure? By the way, it's not a soda. It's a seltzer water. I'm trying to lose weight. We'll see if it works. Probably not. All right. So from there, now let's use this loop and let's switch. We're no longer going to be talking about string Q. String Q is over. Stop trying to make string Q happen. And we are going to take a look at my list. And my list, we have implemented a number of functions. I just realized I may have uploaded the finished version for the, daily activity. Let me check on that, because I want to make sure I didn't do that. Sorry. Thought I had this all squared away before class. Let me make sure. If I did, give me a minute to fix it, and we are going to do the daily activity together. I just want to make sure we're actually doing it and not starting with the finished product. Also, forgive me, my voice is starting to go. Oops. Okay, 1 second. Hang on, I did upload the wrong version of the file. I'll be right back. Sorry. I mean, you can download it, but you'd just be denying yourself that learning experience. It wouldn't ultimately help you understand the material. And I will tell you right now that you're definitely going to want to understand this function before you move on to the homework. You will struggle without it. Uh, all right, sorry about that. I just uploaded the corrected version. Sorry about that. Anyway, so from there, this my list is not a stack or a queue. Rather, this my list is actually a list. Now, I don't implement the full interface list, and it still only contains numbers. But the idea of this is going to have functions, not just push and pop, but things like add, which adds to the end, or get, which is going to get the nth index, or contains, or add, or find, or we're going to have add at a particular location. So we're going to step through all of these and talk about how they work. So let's start with the get function. Now, the get function, the idea is I want to get the value at a particular index. So, for example, I want to get the value at index 4. Now, with an array list, this is easy. You just go to the underlying array and say, give me that array's index 4. But we can't do that here. So rather, we're going to implement this. First, we have some error checks here. These are just to make sure that the index is valid. So if we try to get an index that's less than 0 or greater than or equal to size, that's out of bounds, and we just throw an exception. We don't try to fix that. But the rest of this assumes it's inbound. So first, we create our traveling node, and now here I use a while loop. I could use a for loop here. I just choose not to. I did this as a while loop just to illustrate that this doesn't have to be a for loop. And so, what I do is I loop one step at a time. So t equals head. I then step through, I enter the while loop, and I say, okay, while the index is greater than 0, index is 4, so it is, I'm going to then say index minus minus t equals t dot next. So now index is 3, and t is on the next node. I re-enter the loop because index is still greater than 0, and so on, until I get to here. At this point, index is 0, so I do not re-enter the loop, and I simply return t dot value. So that is going to give me index 4, the value at it. I return t dot value. So count it 0, 1, 2, 3, 4. There we go. So this is the code for get. Are there any questions about this code? As well as an illustration of how it works. All right, let's take a look at a similar function. Let's take a look at find. Find is kind of similar. Isn't a list supposed to order? Not no list order very much matters. You might be thinking of sets. A linked list is still a list. Lists have a first, second, third, fourth, fifth, sixth element. Lists are ordered. They're not necessarily sorted. This is not sorted, but it is ordered. It's a list. It's not a set. Sets don't have order, but array lists, for example, has a get function. This is how the get function is implemented for a linked list. Yeah. So now let's take a look at find. Find works largely the same way, except the idea of find is rather than getting a value at a particular index, I want to look and see not just if a value... Well, actually, here, let me do it this way. Let's start with contains. Contains is a similar idea to get, except instead of... instead of getting a value particular index, I want to check, is a value here? So I'm looking for some target. I just have a standard loop to loop through the linked list. And from there, if t.value equals target, we found it, return true. If I iterate through the whole list and I don't find the value, return false. By the way, a very, very, very common mistake I've seen on the homework is people doing something like else, return false. Here's the problem with doing this, why you should never do this. Because just because the first value that you found wasn't the target doesn't mean the target's not there. So you have to, it's easy to prove something does contain it. If you find one example of the target, you can return true. But you can only return false if every value is not equal to target. So that's why the false is out here. Don't assume you necessarily have to have else return false here, because you don't. From there, this takes us to the daily activity. You actually from there, we now want to implement find. And so with find, the goal is if I have a particular value, or I'm looking for a particular target, what index is it at? If the value is not in the list, return -1. So this is the daily activity, find, which, oops, no one saw that. For now, return -1, this is the stub. Using contains, and hop into Discord, work with each other on this. Using contains, see if you can implement finds. The two will be very, very similar. But there will be some extra things in find. See if you can implement this. So work with each other on this. I'll go away for like 5 minutes or so. And then I'll come back and I will work through this with you. But jump in the Discord. Right now there are 3 people there. I can see who's in Discord. Jump in and see, work with each other. See if you can write the find function for this linked list. And again, I'm going to do it with you, so that's free daily activity progress. But see if you can do it. And we'll be right back. right. Hello, everyone. We're back. So, let me go with my solution, and then certainly we can discuss any questions. So the first thing is, I'm going to start really by just copying and pasting this. Now, I have to make modifications, of course, but let's start with that. Now, I know I'm going to have to loop through every value, and I know I'm going to have some t.value equals target, but the difference is I'm not returning true or false. Instead, if I were to return false on contains, that means the value's not in the list, right? So then I can just return -1, right? Because it's not there. So now I only have to worry about what to return here. That is the index of t. Now there's the difficulty though, because there's no way to go from t to the index easily. But what I can do is I can create an additional field, int I equals 0, to serve as my index. And from there, every time I enter the loop, I'm going to check if t equals, or if t.value equals the target, and if it does, I'm going to return I. Otherwise, I++. And now I tells me the index of t every time through the loop. And that's all I need to do. That's it. We have some tests down here for this. See, I have some tests here for find. Let's go ahead and run this. Make sure my output matches. And I get 6 should be 6. -1 should be -1. Because the same reason we talked about before. So first, a function that returns an int is not allowed to return null, because primitive data types do not have a null value. The second reason is when we're using a find operation, the general common practice is if the value is not found, return -1. That is common across, I mean, even Python's find function behaves that way, and Python technically supports negative indexes. So -1 is called a sentinel value, and it just means the value was not found. Yeah. So now let's take a look at the last method, because this one is going to be pretty relevant to the homework, and it's tricky. This is adding at a particular index. And let me see if I have my slides for that. Hang on. Because these slides actually are missing that. Let me find... Here we know. I just said here we know. I realized that was kind of funny. Give me 1 second. I thought I had the right slides up, but apparently I did not. So I'll just pull up the PDF that I used in the spring, and I'll re-upload this in a second. Because I had an illustration. There it is. Sorry. It's taking me a bit to remember where everything was. Here we go. Okay. So we're doing this with Chrome now. But let's take a look at the add function in this way. And I will upload this slide deck later, because I for some reason don't have this file locally on my machine. Anyway. So, if we're adding at a particular index the value, understand that what this means. If I say add 417, that means I need to put in between index 3 and index 4 of the existing. So 0, 1, 2, 3, 4. I need to put 17 there, in between two values. Right? So that's the distinction. So understand that is our end goal. Now we're going to talk about how we get there. The first thing is we have special cases when we're adding at the end. Right? If I'm adding at index 0 or I'm adding at n. And notice that in this case, I'm saying add at the size, not size minus 1. That's straightforward. I'm just adding to the beginning, which is exactly what we did with push, or I'm adding at the tail, which is exactly what we did with enqueue. So let's take a look at that code. You can see, first, if it's empty, I just say head and tail equals new node. And then at the very end, you see I have this increment size, so that gets covered eventually. Else, if the index is size, I'm adding at the tail. Else, if the index is 0, I'm adding at the head. So that those parts, this shouldn't be new. The hard part for add is specifically adding into the middle. So if we're adding into the middle, then that's where we need a loop. And we're looping through, specifically, if we're adding at index 4, that means we're adding after index 3. That red arrow is pointing to where the insert's going to go, right? So from there, we create our loop. So if we're adding at index 4, we need to loop to where t is not node 4, but node 3. So we're going to loop not to index where we're inserting, but index minus 1. So initially, sorry, I don't know why this says index equals 5. That is incorrect. This should say index equals 4. Apologies. That's just a typo because we're adding at index 4. So if I say I want to add at 4, I'm going to add after 3. So because of that, I don't loop while index is greater than 0 like I did with get. Rather, I'm looping while index is greater than 1 because I want to get the node before the index I'm adding at. So while index is greater than 1, t equals t.next, index minus minus. The order of these two statements doesn't matter. So we loop through simply by saying, okay, now index is 3 because we did minus minus. Now index is 2. We're at the next node. Now index is 1. And now we stop. The loop is over. And at that point, now I'm going to go up to the whiteboard and draw a quick little diagram. Because here's how we need to do the add. So we have our node t. This is the node that we are adding after. And that points to the node that comes after t, which for now is t.next. Right, this is the next pointer. Now at this point, in order to add a node between t and t.next, we first create our new node t. Then from there, we have to do in a very specific order. Ultimately, our end result, and I'm drawing our end result with purple, is this. Our end result is these arrows. Now I have two arrows to draw here, A and B. My question to you, which arrow do I draw first, A or B? Or, if it doesn't matter, type C. Which arrow do I draw first, A, B, or if it doesn't matter, C? Because I haven't drawn either of these yet. But which would I do first? A, B, or if it doesn't matter, C? Got a few answers so far. Mostly B's, actually all B's so far. So this actually has to be B, and I'll tell you why. This is why this has to be B. Remember, T has a node after it. Because if T were the end, my if statement would have already separated out. So we know there's a node after T. If I draw the first arrow, T.next to new node, watch what happens. If I say t.next equals new node, I now have a problem. What is that problem? What is this node now? Is it t.next? No, new node is t.next. So how can I get to this node? I have t. I have new node. Can I reach this node anymore? No, I can't. There's no arrows drawing to it. So if I drew arrow A first, because that's what this was, if I drew arrow A first, now I can no longer access this node. I've lost everything after this point in my list. So I cannot draw A first. I have to first say, and remember we have currently t.next pointing at that node, I have to first say new node.next equals t.next. And that draws this arrow. That was B. Then and only then can I say t.next equals new node. And now this is fine, right? t.next and t.next.next. That's fine. I still have a single chain, right? So if I'm inserting into the middle, I have to put it into this order. I have to do new node.next equals t.next first. New node.next equals t.next first. That is this. And then finally, t.next equals new node. And now I'm done. So this is how you insert a node into the middle of a linked list. So now, I'm going to talk to you about the homework assignment. The homework assignment is called Traveling Salesperson. By the way, we've just did the in-class activity with Find, so you can just submit that. The homework is based on a problem called Traveling Salesperson. And here's how that works. You are a salesperson, and you have to visit a particular number of locations You leave from home. We'll call this red dot home. I should have done a pale blue dot as home. That would have been poetic. But for now, we'll say the red dot is home. And the idea is you want to find the path where you as a salesperson leave from home and visit every address exactly one time such that your total travel time is the smallest possible. So for instance, this might be the smallest. I don't know if it absolutely is, but this is a likely candidate for smallest possible. I can tell you what obviously wouldn't be the smallest possible path. Would be a path that looks like the following. If I did this path, and then this, and then this, and then this, and then this, I can tell you right now, I guarantee this is not the shortest path. Visiting the nodes in this order. The idea of traveling salesperson is I have to leave from home and I have to return home, but I want to visit every location along the way such that my path is the shortest possible. Now, the simplest way to solve this problem is to just try every path. So if you think of these points as A, B, C, D, and E, well, then you could come up with every path as A, B, C, D, and E, A, B, C, E, and D, and A, B, E, C, D, and so on. But this approach is n factorial. And that is the brute force approach, and it is O of n factorial. And this is hilariously slow. It's really bad. Could we use Prim's algorithm? Not to do the homework, although if you want to challenge yourself to do so, you're welcome to try. Prim's algorithm, by the way, I think that's actually for shortest path between 2 points. That's not the same as shortest circuit. So that won't apply here. Prim's algorithm actually won't I don't think will apply here. Because that's if I pick 2 points, what's the shortest path between them? That's different than the shortest circuit. All right. So from there, this approach is pretty bad. Now, there's a technique called dynamic programming, and that has a better runtime. That runtime is O of n squared times 2 to the power of n, which is still exponential. And it's actually worse than exponential. And here's the thing. This is the best solution anyone's come up with. Nobody has beaten this solution, ever. And it's suspected that nobody ever will. I am not asking you to beat this. Rather, what we're going to try to do is we're going to try some heuristics. And the idea of these heuristics is not to find the shortest path. Instead, it's to find the shortest enough path. Because it turns out that there are solutions to the traveling salesperson that get pretty close to the perfect answer in linear time. And really, really close to the perfect answer in, say, quadratic time. None of them get the perfect answer in polynomial time. That's probably not possible. But we can get close. And one of our algorithms that we're going to do actually is going to get really close. You are going to attempt 3 different heuristics. And we're going to walk through them very quickly. The first is to understand how we're going to formulate our solution. Let's say I have 3 points, or 4 points. I have A, B, C, and D. And I'm going to add the points in alphabetical order, A, B, C, D. Actually, let me do, there's a particular way I want to do this, C and D. So I'm going to add the points in alphabetical order. I'm going to represent my path as a linked list. Now, this is where it gets a bit tricky. Because, remember, I always have to start and end at home. And I'm going to add the points 1 point at a time to this tour. So, if, for example, my path were A to B, and B to D, and D to C, and C to A, here is what this linked list would look like. I would have point A. This is my head. That points to point B, which points to point C, points to point D. Oh, wait, no, I did this, sorry, it's B and then points to D. Excuse me. C. And this is going to point to A. And the key distinction I'm drawing here is that the first and last points are actually the same point. Because again, you have to leave from home and arrive from home. On the homework, your linked list, which will not contain integers or strings, but will instead contain point objects, which that's what this is, it's an x and a y coordinate, is your point objects will have your tour, which is what your linked list is called, will have one node containing A for the first, and one node containing A for the last. And all the nodes that you add will be added in between. So to illustrate how we would build this up over time, erase the lines I have now, and let's say that we simply added the points in the most naive way possible. And the way we're going to add those points is we are going to add them just after A. Whenever we have a new point, it's going to happen after A. Initially, my tour is going to look like this. The salesperson walks out their door, and they turn around and walk back inside. That. But then when I add point B, which I'm going to add in, let's go red. When I add point B, the idea is I'm going to go from A to B, and then B to A. And so I'm going to add B immediately after A, although I'm going to draw this a bit weird, and you'll see why in a second. I'm going to create the node B, and then B.next needs to be, in this case, the last, but more importantly, A.next is now B. So this is my linked list. Then I need to add C. So instead, I'm going to add C immediately after A, because that's the naive approach. Just put C right here between A and B. So now my path instead is A to C, and since A was going to B, I need to make C go to B, and then B back to A. So I put C in here, point C, C dot next is the same as head dot next, and then head dot next is C. And then from there, I add D after A. For that one, I'll use green. So instead of going from A to C, I go from A to D, D to C, then C still goes to B, and B goes to A. And that one, I create my node D. D.next equals head.next. Head.next equals D. Now, trivially, this approach is not very good. This will not be very effective. There are other techniques that you will do that improve upon this. There's going to be 3 in total. As you can tell, this is going to be very helpful to draw pictures here. So that's something that we're going to try to encourage. If you come to office hours, is we may have you open up something like PowerPoint. So I want to illustrate how I drew these pictures as they currently are in PowerPoint. All I did to draw these pictures was and you could do this on a blank PowerPoint, new, just delete these, and then you just add shapes. Insert shapes. You can have a box, and this can be some value, and then for the arrows, it's just insert shapes, and then one of these arrows from here to here, and there you go. So if you come to office hours, I will likely do something like this, or I'll just do it on the whiteboard. This is easy to do if you don't have access to an extra webcam and a whiteboard like I do, which I assume most of you don't. But to that end, you can just draw pictures in PowerPoint. I actually do this all the time. A lot of times when I do photo editing, I'm actually just putting stuff into PowerPoint and messing with it there. And then just taking screenshots, which is a very potent way to do it, but it works. So that is homework 5. With that, that is the end of today's lecture. Are there any questions? Otherwise, that was linked lists. And again, all the code that I've done is uploaded, so you can take a look. And I will see everyone next time. Tomorrow, we will start talking about trees. And I do have office hours here in 17 minutes, so I actually need to end right now because I need to get a few things done. I apologize in advance. I have to cut my office hours off at exactly 4:30 today. I will not be able to go later, and it's because I have a meeting at 4:30. But there are TA office hours today, 4:30 to 5:30, and 5:30 to 6:30. So I will see everyone then. Take care.